You receive an email with a PDF invoice attached. You double-click the file, it opens, and you see a completely normal-looking document. But behind the scenes, without you clicking any links or enabling any macros, the file has already compromised your system. In the split second it took for that invoice to render on your screen, an embedded JavaScript block quietly executed in the background. It initiated a heap spray in your computer's memory, creating a runway for a shellcode routine to download and execute a malicious dropper. The victim sees a harmless piece of paper, while the attacker sees an execution environment. To analyze these threats, we have to stop looking at PDFs as documents and start treating them as software. A standard text file is a flat, continuous string of characters. A PDF operates differently. It is a highly complex container designed to hold and execute multiple layers of independent objects. This diagram shows the 4 structural layers of every PDF. At the top is the header, which identifies the file version. Next is the body, followed by a cross-reference or xref table that acts as a map. And finally, the trailer, which tells the PDF reader where to start. The body layer is where we focus our attention. It contains a series of numbered objects, which can be text, images, embedded files, or JavaScript. When an attacker weaponizes a PDF, they embed their malicious code inside these numbered objects. By understanding this architecture, you don't need to open the document to see what it does. You can bypass the visual rendering completely and directly examine the objects hidden inside the container. Attackers can't just throw raw malware into a PDF and expect it to run. They have to tell the PDF reader how to execute it, and they do this using specific action keywords within the object dictionary. This graphic shows the 3 primary attack vectors. We'll start with the first card. This vector relies on the presence of 3 specific keywords working together: JS, JavaScript, and OpenAction. The JS and JavaScript tags tell the reader that the object contains code, while the OpenAction tag is the trigger. Together, this combination executes the JavaScript automatically the exact moment the file is opened, requiring 0 clicks from the user. The second vector uses the launch keyword. This action attempts to execute an external shell command directly on the host operating system. The third vector uses the embedded file keyword. Attackers use this to attach a separate hidden executable file inside the PDF container, prompting the user to extract and run it. Because the PDF format requires these specific keywords to function, the attackers leave a distinct structural footprint. We can hunt for these exact strings to determine exactly what the file is trying to do. To find these keywords safely, we use a Python script called pdfid.py. Think of this tool as an X-ray for documents. It counts dangerous keywords inside the container without detonating any of the payloads. In this terminal interface, we run the command pdfid.py against a file named suspicious.pdf. The tool immediately returns a statistical count of every structural keyword it finds. Scanning the output, we look for our high-risk indicators. Here, we see a count of 1 for /JS, 1 for /JavaScript, and 1 for /OpenAction. This file is configured to run code on Open. Notice that pdfid only gives us the keyword counts. It does not show us the actual code. To perform surgical extraction of the malicious script, we will later use a different tool called pdf-parser.py. Running this single X-ray command is always your first step. It gives you immediate situational awareness of the file's capabilities, allowing you to formulate a safe extraction plan. Let's test this methodology. In this terminal, we ran pdfid against a new file called invoice-v2.pdf. The output shows a count of 1 for the /launch keyword. Pause the video here. Based on this output, what is the attacker's objective and what is your immediate next step? The /launch keyword tells us the attacker is attempting to execute a command directly on the operating system. To investigate, your next step is to locate and extract that specific command string. Diagnosing the exact attack vector is a mandatory requirement. You must know what the file is designed to do before you extract a single byte of data. We can standardize this entire process. By mapping our 3 attack vectors to specific extraction steps, we create a strict triage decision tree driven entirely by the pdfid output. This diagram shows the complete triage workflow. On the first branch, if your initial scan shows /JS and /OpenAction, your immediate objective is to extract the JavaScript object and check it for shellcode or heap spray patterns. On the second branch, if you see the /launch keyword, you skip the JavaScript checks entirely. Your goal is to extract the launch action object and read the shell command string. On the third branch, a positive hit for /embedded file means you must locate the embedded object, extract it, take its file hash, and query it against a database like VirusTotal. This decision tree dictates exactly when and how to deploy pdf.parser.py. You never extract objects blindly. You use the initial keyword hits to target the precise location of the payload. By treating the PDF as a structured container and using PDF ID as an X-ray tool, you maintain complete control of the analysis. You dictate the terms of the investigation, cleanly neutralizing a threat that arrived disguised as a perfectly normal invoice.